Good afternoon. Good afternoon and welcome to today's edition of Science Sundays. I'm John Beacom, Director of the Center for Cosmology and Astroparticle Physics, or CCAPP. So the Science Sundays is a monthly free lecture series that you all know about, obviously. It's put on by the College of Arts and Sciences at The Ohio State University. It's organized by 8 sponsoring centers, of which CCAPP is one. And we try to make these events broadly available for scientists who are active, to members of the public who are interested in what we do, all the way down to the next generation of scientists, the children who are here. And at the end, when we take questions, we'll prioritize questions from anybody under, say, 15. So this lecture series is now in its 5th year, and it's grown every year. There's still seats in the front. Go ahead. Just don't steal my backpack. Today's lecture, we're doing something new and special. We're making a videotape, and it'll be posted on YouTube. This was made possible thanks to a generous donor. We're interested in expanding this program, and if you'd like to help, please contact us. So the Center for Cosmology and Astroparticle Physics has a 3-part mission. One is to explore our amazing universe and all of its even more amazing contents, figure out what they mean. Second is to train the next generation of scientists on that research. Those are our students and postdocs. And third is to help inspire the next generation of scientists, the children, by showing them what a career in science could look like. And for everybody else to satisfy their curiosity of what we're up to. One of our members is Todd Thompson. He's a leader in all 3 of our areas of research, teaching, and outreach. Todd is an internationally acclaimed researcher. He is a winner of the Alumni Award for Distinguished Teaching from Ohio State, and he frequently presents results to the public of all ages. So let's thank Todd, let's welcome him, and we'll take questions at the end.
Thanks very much, John. And thanks everybody for being here. So my title today is The Fantastic Forge. I owe that part of that alliteration to my brother, who can't be here today, but he did contribute by helping me talk about the title. I want to take you on a tour today of the furnaces, the kilns, the forges inside stars, low mass stars and high mass stars. And I want to tell you about their supernovae especially. And there'll be beautiful pictures and some whiz-bang and some movies, but I also want to tell you a little bit about what it's like to be a theoretical astrophysicist. I want to try to bring you a little bit into my world about how I think about astrophysics, what the outstanding questions are, and what the deep mysteries surrounding these particular issues are, and how we're trying to move forward on them. So I thought we'd start with a quote from Carl Sagan. One can hardly talk about the elements in the universe without talking about some of the very famous quotes from Carl Sagan that many of you know. And so I thought I'd start with that. This is a quote from Carl Sagan's Cosmos, in which he says, "The nitrogen in your DNA, the calcium in your teeth, the iron in your blood, and the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff." And indeed, that's true. If you look into your body, you will see that it is made mostly of hydrogen, oxygen, carbon, and so on. And fully 2/3 of your stuff was it didn't just come from a star. It was made in a star. So I'd like to remind you of the periodic table of the element before we get before we get started. I apologize. So let's begin. So here we have hydrogen. Hydrogen has 1 proton and was made almost exclusively in the Big Bang. Here we have helium with 2 protons and 2 neutrons, also made in the Big Bang. Then there are some things, lithium and beryllium, and there's some things you really care about: carbon, nitrogen, oxygen. And we're going to focus on carbon, nitrogen, and oxygen in particular, and we're going to get up to about iron. And if you're wondering about the elements after iron, I encourage you to continue wondering. And feel free to ask me after or even during the talk. The main thing to start with is that our universe was made with hydrogen and helium. The Big Bang gives us a store of gas. And everything that happens after that is the story I want to tell you today. So there are about 100 billion stars in the Milky Way. Our Milky Way is composed of approximately 100 billion stars, all formed over the last 14 billion years of cosmic time. When you look up at the night sky, you see perhaps 1,000, maybe, stars in the night sky. But the diffuse glow you see towards the center of our galaxy is billions upon billions of stars in that direction. Clouds of gas, mostly hydrogen and helium, collapse to form new stars with a range of masses from 0.1 to 100 solar masses. So I'm going to use this nomenclature here of solar masses. So what I want you to think about is the sun is easy, that's 1 solar mass. 0.1 is 1/10 the mass of the sun. 100 is 100 times the mass of the sun. And every year, gas is converted into stars in our galaxy. So our galaxy you should think of as this plate of orbiting gas, dust, and stars. And every year, some of that gas collapses because of the force of gravity to form new stars and collections of new stars like this beautiful star cluster. And their stars are always born with a range of masses. Some stars 1 solar mass, some stars 2 solar masses, some stars 5 solar masses, some stars 100 solar masses. And they have different evolution and different structure and different consequences for our physical world. So for example, most stars are like the sun. Many of the stars you look up, you see in the night sky are like the sun. And the most common type of star is a bit like the sun. And if my first question is, can you explain them? How would you explain them? How would you explain a star? You need to explain at least several things. First, its structure. Second, its energy loss and energy production. And third, its lifetime and its evolution. You'd like to explain all simultaneously. And how are you going to do that? Okay, well, as a theoretical astrophysicist, what you do is you first make some hypotheses. You first observe. You observe that the star is neither expanding nor contracting rapidly. And you say, well, I'm going to guess that pressure balances gravity everywhere. In this ball of gas, just like in you right now, gravity is pulling downwards. Gravity is always trying to make you fall. And you hold yourself upright against gravity, okay? Using your energy, your source of energy. For me, that source of energy is yogurt. I eat yogurt in the morning, for lunch, and in the evening, and as I do, I get energy, and my body takes that energy, and it allows me to keep myself up. A star has a different power source. It's not yogurt. It's instead a huge ball of hydrogen and some helium and some trace elements that always, 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 at every point on its surface, at every point in its inside, wants to fall in. But instead, everywhere, it's supported. And it's supported by pressure. That is, the gas pressure. Okay, so we're going to first say pressure balances gravity. And the second thing we're going to hypothesize is that the energy source is hydrogen fusion in the core. And we're going to deduce implications of that. So the first is that the outward push of gas pressure balances the inward pull of gravity. And this is something I remind my students of, several of which are in the audience, and I will tell you now, because you might not think that you could do theoretical astrophysics. You may never have done theoretical astrophysics in your life, and indeed there are some aspects of theoretical astrophysics that are very complicated and take a while to learn. But when you write down a sentence like this, the outward push of pressure balances the inward pull of gravity, I want you to see that you're incredibly close to making an equation. You're very close to making an equation. Well, if you're just bold enough to write that down, you've written an equation. And so the first thing I want to say is that oftentimes a simple declarative sentence is an equation that you can then turn into something that you might not have believed was even possible. For example, this says that the outwards force equals the inwards force. I always tell my students when they know something like that, they should write it down. Because if you just take an equation like that, you can expand it a little bit. You can add in the little pieces. You could say, well, that inwards force is gravity. That's going to have something to do with the mass and size of the body. It might have to do with some physical constants of nature. Whereas the left-hand side of that equation says the force outwards, which is this pressure, this hot gas. If you take a flame and you heat the gas in this room, the pressure will increase if its temperature increases. If you increase its density, its pressure will increase. And many of you might even already be having flashbacks to high school chemistry when you learn something like PV equals NKT, or P equals nRT, or PV equals nRT, or P equals NKT, or something like that. But there were T's and densities and so on that related pressure to temperature. And so we could take this, and I want to show you how easily it is to deduce something you didn't already know. If you say that the outwards pressure, the outwards force is pressure times area, it's like a balloon. Imagine a balloon. You have gas inside the balloon that's pushing out against the balloon. The pressure times area. And then you take mass times acceleration, which is the definition of force. Newton said F equals ma, F equals mass times acceleration. And then you write down the area for a spherical star, which is 4 pi r squared. And you write down the mass, and the acceleration you write down as the gravitational acceleration. This one you need to know some physics to do this. Okay? But I just want you to see something. If you know the radius of the sun, and you know pi, and you know 4, and you know big G, which the Google will tell you, and you know the mass of the sun, which we do very well, you can invert this to find the pressure at the core of the sun. It's really that easy. And if you do that, you will deduce that the temperature in the core is approximately 10 million degrees Kelvin. The surface temperature of the sun is 6,000 degrees Kelvin. The temperature in this room is a few hundred degrees Kelvin. But the core, just from this simple theoretical argument, this is pure theory here, we assert a principle, which is what technically is called hydrostatic equilibrium, but outward pressure force equals inward pull of gravity, and we deduce something that I bet many of you did not know. We'll come back to that. Then we say hydrogen fusion in the core. Well, how does that actually happen? Hydrogen, what is hydrogen? Hydrogen, forget about the electrons. We don't care about the electrons. We don't care about electrons for this entire lecture. Electrons are for chemistry. Okay? A hydrogen is just a proton. And we want to take a bunch of hydrogens and we want to make them into something with fusion. How are we going to do that? Well, the first problem you run into is that like charges repel. So if you want to get protons together to do something, you have to work very hard because they're two positively charged particles. You have to bring them together. And that takes an incredible pressure, an incredible force to do that. If only you had such a big force around, maybe you could get a bunch of these hydrogens together and turn them into a helium, but then you have a different problem. And that's, you remember that helium has 2 protons and 2 neutrons, okay? But you only have protons on this side. So how are you going to take protons and convert them to neutrons? And supposedly you're going to have energy because after all, when we walk outside on a sunny day, maybe not this sunny day, it feels warm, okay? So how to get protons to combine, how to change protons into neutrons, and where does this energy come from? And so here's the amazing thing. There are a bunch of amazing things. First, you find that if it is hot enough, protons can actually get close enough to fuse. If you want to fuse, the reason why fusion is not happening in this room is because it's not hot enough. It's probably not dense enough too, but it's not hot enough. Okay? And if you could only heat this room up to 10 or 20 million degrees Kelvin, we might be able to have fusion. That we would die instantly, but anyway, you would at least have fusion. Okay? And what you find is the same number. In order to get protons to fuse together, you need to be hot, about 10 or 20 million degrees. Next you find protons can change into neutrons in a nuclear reaction by emitting an anti-electron and a neutrino. Okay? And the details of this are actually quite complicated. In fact, these couple words right here, prediction and confirmation, could be their own talk. And in fact, John Beacom, who's here, is an expert in this issue exactly. So let me break it down slightly. If you change a neutron, if you change a proton into a neutron, you produce this thing called a neutrino. Right now, there are millions of neutrinos flying through every square centimeter of your body. Millions of them. Every square centimeter of your body from the sun. They're going right through you, right through the Earth, and they're all produced by fusion at the core of the sun. And so here's the thing, if you believe that the sun is powered by whatever this reaction is, then you assert that in the process of changing protons to neutrons, you emit a neutrino. And if there are neutrinos coming through right now, millions of them per second, you might be able to detect them. And that makes a prediction. Okay? And this is the kind of thing I look for when I'm doing theoretical astrophysics. I think first I'll do an estimate, like the estimate I showed you, that says the core temperature of the sun is 10 million degrees. Then I find I need to make a prediction, which is there are neutrino after neutrino after neutrinos coming through this room right now. And then I can confirm that prediction by actually detecting those neutrinos. Where does the energy come from? It comes from nuclear binding energy. Helium wants very much to form. if you can get the atoms close enough. Okay? And where does this energy come from? This nuclear binding energy. I want you to imagine that you have particles, and if they get together, they kind of fall together and release energy. Not unlike this book. Is the book bound to the earth? If I let it go, what will happen? But what will happen to the energy? Good. The energy comes out. You're exactly right. The energy comes out. The energy comes out in the form for this book of sound, vibration, a tiny bit of heat. Most of that vibration is absorbed by everyone here in the room and by the room itself. In this case, the nucleus wants to form badly if only it can get in the right conditions. And when it does, it radiates energy in a way analogous to how that book fell. So the helium wants to form and is strongly bound. And this energy, this most famous equation in all of physics, which is that energy is directly related to mass by the speed of light squared, gives you a way to convert some of the energy in this interaction, some of the mass in this interaction into energy and vice versa. And this implies that the lifetime of the sun will be 10 billion years, and it implies that this interaction can be better written as 4 hydrogens, that is 4 protons come together to make a helium nucleus, produce energy, and produce neutrinos. And I want to highlight these neutrinos because this is how you know that I'm not making this up. I'm telling you stuff about the core of the sun. We derived that the core of the sun, you and I together derived that the core of the sun was 10 or 15 million degrees Kelvin. Why should you believe that? Why? You should believe it because we can do a test. We can look for the neutrinos that come out of this and related interactions that are happening in the sun right now. And we can see that there's literally a one-to-one correspondence between every single neutrino that comes out and every fusion interaction that happens in the core. And that's why you should believe me. Now, what happens after hydrogen fusion? After hydrogen fusion, it turns out there's helium fusion. So the star eventually runs out of hydrogen. Star starts with a certain mass, say 1 solar mass like our sun. It burns through the hydrogen. Where does the hydrogen go? Well, it goes into helium. What does the helium do? Nothing. Helium sits around. Nothing happens to the helium for a while. It's only when the star starts to run out of hydrogen that it collapses and gets hot enough to burn helium. And why do you care about that? You care about that because you care about carbon and oxygen. This is the first time carbon and oxygen makes a step. We've taken one step on the periodic table from hydrogen to helium, and then from helium to carbon and oxygen. If you take 3 helium nuclei, you can convert them via a series of interactions into carbon and oxygen and energy, and yes, again, more neutrinos. And this is actually the end of the story. It's actually kind of a boring story for low-mass stars. Low-mass stars like the sun basically ends here. The star, at the end of forming a carbon-oxygen lump in the center, nothing happens after that. It throws off its outer layers, and it makes fuel for new stars. So here's a picture of a star with a central white dwarf and an outer layer blowing its outer layers off. And this thing is this white dwarf I'm going to refer to as made of pure carbon and oxygen. And what happens to that carbon and oxygen? It does nothing. That white dwarf basically cools off for all eternity in space. If you chuck it into space, basically it starts out hot, cools off more. Similar to what would happen to you if I threw you into space. Okay? You start off warm, you cool off very rapidly, and then you cool off more. Okay? And that happens forever. And a star like the sun leaves behind a 0.6 solar mass white dwarf. Well, why is that number interesting? That number is especially interesting because it leads to the first sad story in all of astronomy. There are actually many sad stories in astronomy and astrophysics, and this is the first sad one. Imagine you start with a universe filled with hydrogen and helium. Okay? And then the hydrogen-helium form stars, and that'll leave behind this thing called a CO white dwarf. And every time you make a 1 solar mass star, you leave behind a 0.6 solar mass white dwarf that does nothing. Well, that means that 0.6 solar mass white dwarf just sits there forever. The 0.4 solar masses gets flung back off and gets incorporated into a new generation of stars. But you can see very quickly that the universe runs out of gas. The universe does run out of gas. The universe starts with a supply of hydrogen and helium from the Big Bang, and it works its way through it. The total amount of gas in the universe is decreasing because objects like this white dwarf are forming, and they do nothing. Okay? Nothing at all. And that's the end of the nucleosynthesis, or the production of the elements in low-mass stars. Now there is one way, an important way, for this white dwarf to undergo a transformation, a transmigration. It changes from one thing into another thing. And this happens when you do what what my observer friends do, and you look out into space. Okay, so far we've been talking theoretically, but if you look out into space, do you know what you see? You see white dwarfs exploding in gigantic supernova explosions called white dwarf supernovae. Okay? And so this is the way you can make another step. You take a normal one solar mass star, like the sun, it does this thing, it does hydrogen fusion, it does helium fusion, leaves behind this carbon-oxygen white dwarf. What happens if that star is in a binary system with another star? Okay. So imagine, if you will, that the sun is not a single star, but instead a binary star, two stars evolving. And then the sun evolves, and it becomes a white dwarf, like this little guy right there. That little thing is a white dwarf next to a very famous star called Sirius in the night sky, one of the brightest stars in the night sky. And Sirius has a buddy, and that's its white dwarf buddy. And this star already evolved, already did what I just told you, already burned through its supply of hydrogen, all the way through its helium, and produced this carbon-oxygen white dwarf. And the question is, what will happen when Sirius swells up at the end of its life? It might dump some matter from itself, like this artist's depiction. This is an artist's depiction. Most of everything I'll show you is a picture, but this is an artist's depiction of a star. And there's a white dwarf here that's stealing matter from its buddy, okay? And we call this process accretion, as if stuff is gathered onto the white dwarf. So I want you to imagine there's a white dwarf, it's in a binary system. It accretes all this matter, okay? And it gets bigger, because matter's landing on it. And it gets bigger and bigger and bigger, from 0.6 solar masses up to 1 solar mass, over 1.1, 1.2 solar masses. And if the mass gets up to a special mass, there is, it turns out, a maximum mass for white dwarfs in nature. If it gets up to this special mass, a little bit above 1 solar mass, about 1.4 times the mass of the sun, it could initiate thermonuclear explosion. And this CO white dwarf that was going to do nothing, just like you in space for the rest of eternity, could be converted into pure iron in a few seconds. You take an entire star, entire half a solar mass or 1 solar mass of material, and you convert it from pure carbon and oxygen into iron in a second. Okay? And that's important for us because you have iron in your body, and you would like to know where it comes from. And if you go and talk to our observer colleagues, you find that hundreds of these white dwarf supernovae are seen per year. Here's one, outshining its entire host galaxy. This is a supernova. And in fact, the observations of these beautiful supernovae that light up the night sky are consistent with the theory of an exploding white dwarf, consistent with the idea that you incinerate a white dwarf. Okay? But the story I just gave you, the story of a big star swelling up and dumping its matter onto a binary companion, is wrong. It's wrong. Okay? How do we know that? Or at least we know part of it's wrong, or at least in some circumstances. I'll just give you some idea of this. So here's a cool movie. Okay, let it play again. And what you're seeing here is that imagine the story I just told you was true. Remember, you're a theoretical astrophysicist now, so I want you to think that way. Imagine the story I just told you was true, and that there was a white dwarf over here where the star is, and it was accreting matter from its companion star that's here. You'll see it's undisturbed at the beginning, and then is violently disturbed, okay, when it'll reform here, right there. That star is donating matter onto this, but then that star gets so big that it then explodes, like I just told you, the story I just told you. If that were true, then we would expect this big boom here to rip the outer layers of the hydrogen off of this star from the companion. Okay, so here's the thing. If you're going to be a theoretical astrophysicist and you're going to say, how can I turn a white dwarf from just pure carbon-oxygen stone into pure iron in some big thermonuclear detonation, you might say, I could do that in a binary, and then you immediately run into this problem. The supernova should rip off the outer layers of hydrogen from the companion, and yet when we study, and we look very hard, and people in this room, in fact, have looked exceedingly hard for this hydrogen, none of that hydrogen is found. And I say, bah, not because I'm frustrated, just because it's a good idea that doesn't seem to work. And you might wonder if there's another way to trigger an explosion that doesn't involve this hydrogen. And there is. So theorists, this is what happens. Theorists go and they try to think up ways. And in fact, most of my job is to sit and imagine ways in which nature could produce the thing that is seen. The observers see things. They are exceptionally good at seeing things. They see new things all the time. And then I try to figure out how it works and why it works using the equations of physics and using simple declarative statements like we started with. Force outwards equals force inwards. Okay? And the theorists have come up with the following idea, that if you really wanted to make a white dwarf explode, but you didn't want any hydrogen to be around, maybe you just say, there's not a white dwarf and another star, there's two white dwarfs. Two white dwarfs that somehow merge together. Okay? And this is just showing a simulation from Raskin of two white dwarfs merging together, our theoretical picture of how two white dwarfs would merge together. There's a bigger white dwarf and a smaller white dwarf, and they merge together, and the idea is that when that happens, and it should happen a lot, in fact we see these binary white dwarf systems, and we see that they should merge, the idea is that maybe that will trigger a supernova. And unfortunately, the jury's out. We don't really know. Or fortunately, depending on your perspective. The theorists don't really know whether this will in fact trigger a supernova. An idea people are just exploring now is that a white dwarf binary in a triple system, actually with another star, if you can imagine it, two white dwarfs going around each other, and a third star going around that, might actually cause these two white dwarfs to physically collide into each other, and that might trigger an explosion. And why are we doing this? We're doing this for a couple reasons. One, we'd like to know the origin of iron. Two, we'd like to be able to explain these massive supernovae we see all over the universe going off every night. Okay? And so the question is, how is the explosion triggered? We see these CO white dwarfs, we see these white dwarfs exploding, and they're completely consistent with the idea that somehow, some way, a white dwarf was exploding, okay, into iron. But we don't know how the explosion is triggered. What are the stakes? Most of your blood, most of the iron in your blood, most of the iron in the universe comes from here. So when you look at the red of your blood, if you prick your finger, those iron atoms came from this type of a supernova explosion. This is actually exploded white dwarf guts in a supernova that was seen by Tycho Brahe. So the supernova was seen. Tycho Brahe, the story says he was walking home, and he looked up in the sky and saw what he thought was a new star. And we train our biggest, most awesome X-ray telescopes on this region of sky right now, and this is what we see, which is hugely iron-enriched explosion guts of a CO white dwarf. And you would like to know, was it another binary star? Was it two white dwarfs that merged together? Was it the third star? And we don't know the answer to that. The answer at this moment is, I would say, completely up in the air. All right. I want to change from low mass stars to higher mass stars. And I show Orion because Orion is spectacular. Orion is up right now. You can see Orion. Orion is emblematic of almost everything and every stage having to do with massive stars. Orion, if you look closely, has a beautiful star-forming region right there, a bunch of gas collapsing to form brand new baby massive stars. Here is Betelgeuse, the right shoulder of Orion, a massive star that may explode tomorrow, maybe exploded 600 years ago, and we'll see it tonight. May not explode for 1 million years, but you certainly have better odds of that going off in the next week than you do of winning the Powerball jackpot. There's Bellatrix, which is a massive star. There's Rigel, which is a massive star. There's the belt stars, Mintaka, Alnilam, and Alnitak, which are all massive stars. Some of them, in fact, in triple systems, binary systems, and so on. Okay. So what's so interesting about stars that have higher mass than one solar mass? Why would that be interesting? You don't understand why it's interesting, you just need to know one piece of physics, which is that if you want to fuse elements, it needs to be hot. And if you want to fuse heavier elements, it needs to be hotter. Okay, so if you want to fuse hydrogen into helium, okay, you need to be a certain temperature, okay? And if you want to fuse heavier elements into yet heavier elements, you need to be hotter than that. Okay? And massive stars can reach high temperatures in their cores, and they do exactly the same things when they form. So this is 10 times the mass of the sun. So for example, Betelgeuse is about 20 times the mass of the sun. It starts with a whole bunch of hydrogen and helium, and then what does it do? It takes the hydrogen and converts it to helium, just like I showed you before. then to heavier elements, up to iron. It takes that helium at the end, when it runs out of helium in its core, it takes that helium, converts it into carbon and oxygen. And instead of that being the end of the story, instead of that being a carbon-oxygen white dwarf that just cools off forever, like a stone in space, it keeps going. Okay? It goes up to heavier elements all the way up to iron. Okay? And one massive star per century or so dies in the Milky Way. Before they die, most get huge, red, and luminous. So Betelgeuse is a very evolved star and could die, should die, in the next approximately 1 million years. So you have a chance. A massive star on its last day. So here's a cartoon of what a star looks like. We call this the onion skin structure of a star before it dies. Okay, so let me start. Imagine there were none of these layers here and it was just hydrogen. If there were none of these layers here and it was just hydrogen, what would it be doing? It would be fusing the hydrogen into helium in its core. But then afterwards, it would take that helium and it would fuse it into carbon and oxygen. And after that, carbon burning into neon, and then neon burning into oxygen, and then oxygen into silicon, and then silicon finally into iron. And if you could think back to the periodic table, no need to have it memorized. But there was sort of hydrogen and helium and lithium, beryllium, and carbon and nitrogen and oxygen. And then it went up, and then somewhere sort of in the middle top was iron, 26 protons. Not very far up, actually. And this is what a massive star does. And why does it do this? It does this because of the things I mentioned before. Gravity is always, always trying to win. Just like you. If you trip on your way out of here, gravity will try to win. Okay? It will try to pull you down. All right? So gravity is pulling everywhere, always inwards. And if there isn't, all of a sudden if you just shut off the fusion supply, the star would immediately start contracting and it would start heating up. And every time the star runs out of a certain fuel in its core, some transformation takes place. It has to get hotter and denser, and it can then ignite new fusion processes. So not just hydrogen into helium, and then from helium into carbon and oxygen like a low mass star, but it can go further. And it can go further because it's hotter, it can go further because it's denser, and all of those are just because of the mass. You were born with a certain mass, but then you got bigger, and then maybe you get smaller, and at least for me, bigger and smaller and bigger and smaller, okay, every 6 months. A star is born with an initial mass. Something about those gas clouds collapsing gives it an initial mass, and that basically dictates its future evolution. And the things I want you to notice here are carbon, oxygen are right here, including the elements of existence, namely your fats, right? Your sugars, C6H12O6, glucose, monosaccharide. Where's that C6? There you go, C. Where's the oxygen? There. Okay. Where's the hydrogen? Well, the hydrogen is where we start out with, and the star will eventually eject all this hydrogen. Okay. And I love this quote also from Carl Sagan, and since I was going through Carl Sagan quotes, I decided to include it. If you wish to make an apple pie from scratch, you must first invent the universe. And it's true. You need to start with a bunch of hydrogen and a successful Big Bang. You need to let massive stars form from clouds of gas in galaxies. You need to let them evolve, forming hydrogen to helium and so on, all the way up, and then you need to let them die. And only then can that material be ejected and form new stars and planets and people who are interested in apple pie. All right. Now I want to talk to you about the last few seconds, really the last moments of this massive star. Okay. Massive star on its last day starts with a big ball of silicon in its core. And what is it doing? It's taking those silicon atoms and pushing them together to make iron. And why is it doing that? Because gravity makes it so. It drives its temperature to such an extent that the silicon has to fuse into iron and is trying to hold itself up in hydrostatic equilibrium, trying. Okay, and in one single day, it converts its entire core, about 1 times the mass of the sun, or maybe 2 times the mass of the sun, from pure silicon into pure iron. And when that happens, it reaches a horrible impasse. And the horrible impasse is that you may not go beyond this. At least normally in a star, you can't take iron nuclei and put them together and get energy. In all the other phases before, remember I even wrote it down, I had a bunch of hydrogens and then a helium and then I had energy and neutrinos. Okay, and the energy is what's holding the star up. Okay, but in this case, you don't get any energy out. If you try to fuse iron together, it won't work. You'll get it. You can't liberate any more of that nuclear binding energy I told you about. And the iron nuclei begin to dissolve as it gets hotter and hotter and hotter. And the whole thing collapses because gravity always wins. Gravity always wins. Somehow, that collapse leads to an explosion. Okay. And how do we know that? We know that because we see massive stars explode. We see individual massive stars like you see Betelgeuse. We see them, and then later, we watch them die. Okay, and this is a picture from the southern hemisphere, which shows the large and the small Magellanic Clouds. And in particular, a star in this particular little satellite galaxy to the Milky Way exploded in the late 1980s. And we watched it die. And this is it. So here's a star known to be, roughly speaking, about 18 times the mass of the Sun, in the range we would think would go through all of the evolutionary stages I just showed you, and which should die at the end of its life, and which looked a little bit like Betelgeuse. The astronomers in the room will say that it was blue instead of red, true, but anyway, we knew that it was an evolved star. And this star gets to the end of its life, and here, February 23rd, 1987, I was 12. It exploded. Okay. And we saw the light emitted, and we saw the star die, and we've been following the evolution of that supernova since. So we know that massive stars die. And we're not the first to see a supernova. Many have seen massive star supernovae before us. In 1054, the Chinese, during the Song Dynasty, saw a new star in the sky, just like Tycho saw a new star in the sky, except this was not a low-mass star that turned from a white dwarf into a supernova. It was a massive star that turned into a supernova. And we know this because if we point our telescopes at the location where this bright guest star was seen in the sky, which was visible in daylight for 3 weeks, we see the inside exploded star guts of a massive star, rich with oxygen, iron, and other elements. Betelgeuse, you can look for it tonight. Okay, it's still up. Its supernova would be as bright as the full moon for weeks. Could happen. Could happen anytime. Hopefully in the winter, and that way we'll have something like not night for several weeks. All right? Should be watching. So what's ejected? We see these supernova remnants, that's what we call them, supernova remnants. The exploded star guts. Technically, we don't say exploded star guts. We say ejecta. This is a picture of the ejecta from a exploded massive star. Went off in sort of the mid to late 1600s, called Cassiopeia A. And the thing I want to show you is that this particular picture is a picture of silicon. We can take a picture of the silicon atoms and the oxygen atoms flying outwards. And so if you wonder, and you should, where the silicon in your iPhone comes from, your cell phone, it comes from here. It comes from this. Now this is flying out at 20,000 kilometers per second, so we only need to multiply that by 3,600 to get kilometers per hour. This is a big number. I don't know, 70 million kilometers per hour, something like that. And so this blast wave goes flying into the galaxy, and all those silicon atoms get mixed up with the rest of the galaxy over time. And that's what we see when we look out at the galaxy at large. We see supernova remnants overlapping on top of other supernova remnants, and all of these metal-rich, silicon-rich, oxygen-rich material flying out into space, overlapping with the other material that's already there, the hydrogen and the helium, and then that coalesces into new stars, new planets, and new people with their deep interest in apple pie. So what's left behind? Well, there are lots of things that are left behind. There's first the guts, the ejecta, which you see blowing out here. And there's also sometimes this thing called a neutron star or a pulsar left in the middle, sometimes a black hole, which you may want to ask me about. My job, I have a bunch of jobs, but one of the things I do is I try to make supernovae happen. So one thing I do is I sit around and I try to imagine physics that could explain how these massive stars explode. And in order to do that, it's quite like the Carl Sagan quote, in order to make an apple pie, first you have to invent the universe. In order to figure out how massive stars explode, we have to begin from the beginning. we first have to understand how massive stars evolve, which I summarized in one diagram about how hydrogen is converted into helium, helium into carbon, oxygen, and so on. Then we need to write down all the equations that describe this physics, and they're equations that can be stated as simple declarative sentences like I showed you. These forces balance. But another one is like energy. Energy is conserved. The energy going into the system is equal to the energy coming out of the system. Momentum is conserved. Okay? Momentum going into a system is equal to momentum coming out of the system. We write down those equations. Then we write down some special equations about how matter behaves at high temperatures and densities, how fluids flow, and how exotic particles like those neutrinos I mentioned interact with matter. We then solve the equations and see what happens. We make predictions and we compare with observations. And our best guess right now is that when that iron core is collapsing, when it's finally lost its final battle with gravity, we believe, or we think that, I won't say believe, our guess is that an intense stream of neutrinos from the neutron star heats the matter so much that it explodes. And I write down this chemical reaction here because many of you have heard of neutron stars. Neutron stars are actually the things that form in the center of the massive star during the explosion. And you might wonder how all of this matter gets converted into pure neutrons. And I wanted to show you that if you have iron, iron is composed of neutrons and protons and electrons. And you're going to get rid of all those protons by combining them with electrons. You take an electron, you combine it with a proton, and you make a neutron. And you also make a neutrino. This is the second time that neutrinos have raised their head in this talk. The first time was as experimental proof that fusion is going on in the center of the sun. And here, it's that we predict that when the iron core collapses, all of these electrons should combine with protons, should leave behind a neutron star, and should radiate a huge number of neutrinos. And the number of neutrinos radiated should be something we can predict because we know how much iron, how many protons and electrons there were when the thing collapsed. And so here's a movie of that. And what you're seeing is you're seeing the inner 300 kilometers of a massive star. Now, massive stars are very big. Betelgeuse is gigantic. Betelgeuse would take up a good fraction of the solar system. Okay? It's huge. But I'm showing you the inner 300 kilometers, a few hundred miles. Okay? And this is the center of the star right here. And what you see in the beginning of the movie, which we'll replay again in a second, is that all the matter comes falling in. And you see these green things falling in, falling in, falling in. This is what happens when gravity wins. When gravity wins, things fall. Okay? And so at the beginning of the movie, which I'll show you will happen now, so there's going to be an explosion, and I will start over the movie. Everything falls in, boom, forms a little baby neutron star here. Neutrinos are streaming out. Okay, matter is falling in. Okay, there's so many neutrinos streaming out that you see this thing, convection. It's like a pot boiling. And then all of a sudden, after about a tenth of a second or a couple tenths of a second, there's an explosion. That's the explosion that's left behind. So here's collapse. And I'll let you watch it again. There's boiling and roiling. Matter falling in. And then boom. 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 There it goes. All right. And that shock wave will then propagate through the star. Remember, I only showed you the inner 300 kilometers before. But that shock wave that just got pushed out by that neutron star that was just energized by all those neutrinos flies outwards at amazing speed and it disassembles the star. It's really quite beautiful. These are supercomputer simulations that show you over a few thousand seconds, 10,000 seconds, but not so long, some hours, how the star is disassembled, taken apart by the explosion. And all of that is powered, at least in this picture, by these neutrinos that are streaming out from the central core. You have neutrinos, of course, like I said, millions and millions passing through every square centimeter of your body, but none of that is happening to you. And that's good. Okay, and the reason is that you're not nearly as dense as this region down here. This region, the densities where I was showing you, where those neutrinos are doing their interactions, are 1 trillion or even 100 trillion times your density. Your density is the density of water. It's 1 gram per cubic centimeter. This matter is 100 trillion times or 1 trillion times more dense than that. And that's why the neutrinos can do such damage. The question, how do massive stars explode? The stakes The oxygen in the air you breathe, the water you drink, and the sugar and the fat you eat comes from here. You've heard the law of threes? Law of threes. You can live for 3 weeks without food, 3 days without water, 3 minutes without air, 3 seconds without hope. Oxygen plays a vital role in probably all of those. Okay. The food, the water, and the air. The answer is unknown. I made it just look like it was known because I showed you some simulations that exploded. I showed you simulations that actually worked. Okay? Truth is, I did that mostly for pedagogical purposes and also because it's no fun to show you duds, things that don't do anything. The truth is that most of the models fail. Model after model after model actually fail. And you know what happens? They all form black holes. Black hole formation. None of them explode. None of them form a neutron star at the center. None of them eject all of this iron and oxygen-rich matter. And why is that? I don't know. We're wrong. Stars explode. We see them explode. We're looking for a good idea about how to make them explode. I said our best guess was this intense neutrino flux. Doesn't mean it's right. Okay? And you would say, why should I believe anything about what you just said if your models fail to explain the supernovae? And I can give you one good reason. When that supernova went off, when that supernova 1987A went off in February of 1987, we saw the neutrinos, we detected the intense neutrino burst. And the energy of those neutrinos, the time it took for them to be emitted, okay, and the total amount of energy we received in neutrinos, all almost exactly matched our expectation from these models. So the models that predict the neutrinos that we saw from a supernova that actually exploded failed to produce the supernova. That means that something's missing. What's missing? I don't know. I don't know. And I would claim that most people don't know. I want to take a moment because we're at Ohio State and because John introduced me and say that Ohio State Astrophysics, we are a leader in these fields. We have some of the world's experts in stars and stellar structure, in neutrinos, and their interactions, in supernovae, the observed properties of supernovae, supernova remnants, nucleosynthesis, the origin of these elements that I've been talking about, observations and discovery. I've been focusing on the theory, but I want you to know we have a cadre, actually quite a large group of people. And to give you 2 quick examples, we right now are engaged with Professor Chris Kachanik as the PI, looking for the first search for massive stars that collapse to black holes. You might think that we've seen stars collapse to black holes. No, we have not, and we are looking for them. And also the most successful survey for bright supernovae of all types, PI'd by Chris Stanek and also Chris Kachanik. Chris Stanek is in the audience here, with John Beacom and myself cheering from the sidelines. The most successful survey for bright supernovae of all types and other explosions is also housed here, is led here by Ohio State University. That's called the All-Sky Automated Search for Supernovae, ASIS-SN, or Assassin for short. And we're all supported by and take some inspiration from the people and resources at the Center for Cosmology and Astroparticle Physics here at Ohio State. I want to summarize and remind you. The Big Bang starts with hydrogen and helium. Fusion in stars makes heavier elements, and then those elements are ejected. When you think about a galaxy, this picture is a beautiful image of Andromeda, but if you want to, you can envision our own Milky Way. In the time it takes the sun to go from here and to go all the way around to orbit once, it does so in a couple 100 million years, there are millions of supernovae that go off. So in your little lifetime, your 100 years on Earth, you may be lucky enough to see, say, Betelgeuse explode. You may be lucky enough to see one supernova explode because one happens per century. But if you put on your goggles that let you live for 100 million years and watch one complete orbit of the sun go around, you would see millions, each one injecting solar masses of silicon and oxygen, and for the white dwarf supernovae, iron. And that would all be enriched into the medium that then makes the next generation of stars, and the next generation of stars, and the next generation of stars after that. In the 10 billion years that we've been around, about 10 billion new stars, about 100 million supernovae billions of suns where the elements ejected, and that's for future stars and planets. There are many mysteries. I've highlighted a few of them. I can discuss them more if you like. The mechanism of white dwarf supernovae we do not know. We know that it's consistent with the incineration of a white dwarf, thermonuclear detonation, but we don't know how it's actually triggered. Massive star supernovae, I showed you some pretty movies, but the movies mean squat if they don't actually conform with reality, and right now most of our movies and most of our simulations fail. The origin of the elements above iron, I haven't even touched on the origin of elements above iron, and you might wonder, where does gold come from? That's a good question. There are many other mysteries too. The answer, what do we need? We need new ideas. We need new ideas and we need new data, the type of data that are provided here by the Assassin Survey and by others. Now when I showed you that first quote by Carl Sagan, many of you might have been thinking, wasn't there another quote? I swear I remember another quote about star stuff. And you're right, there is one. It goes like this, a little longer, I'll read it. The surface of the Earth is the shore of the cosmic ocean. On this shore we've learned most of what we know. Recently we've waded a little way out, maybe ankle deep. And the water seems inviting. Some part of our being knows this, the cosmic ocean, where we came from. We long to return, and we can, because the cosmos is also within us. We are made of star stuff. We are a way for the cosmos to know itself. I recently had a student from one of my classes who asked me as part of his philosophy course to fill out a form answering some questions. And one of the questions was, does your work give you any other different appreciation for the universe than someone else? And I thought, well, maybe it does, you know. So there are two things. The first thing is the sort of the size of space and the isolation, I think, of the Earth and the very vast distances between things. Okay. But also there's a certain connectivity to the rest of the universe. And this is embodied not just in Carl Sagan's quote here, but in other Carl Sagan quotes and in other quotes by Neil deGrasse Tyson. You can go and you can Google the most astounding fact, and Neil deGrasse Tyson puts it better than I will. But what he says, and what I want to say, and what Sagan said before me, is that you should feel a deep connection between yourself and the stars, yourself and the universe, because you are star stuff. A very, very large fraction of everything in your body came from stars, and the rest came directly from the Big Bang. So I've tried to communicate some of that to you, and I hope you've enjoyed it. Thank you very much.
Okay, let's have some questions for Todd. Let's see. Well,
Yeah.
there we go. This little fellow here. Go ahead. And Todd's going to repeat the question.
Yes. So if you try to push the two irons together...
Repeat the question.
So the question is it possible for the iron to fuse together if the star was maybe massive enough, or if there were some extreme conditions? Could the iron fuse together? And the answer is you can fuse it. You could kind of push two irons together, but you won't make a heavier nucleus. What happens is actually the whole thing will kind of dissolve into a bunch of gook. You know, some helium nuclei, some protons and neutrons, and you won't get that bang out. So you can, in fact, fuse it. It just won't fuse into the way we talk about fusion. It won't make a bigger nucleus, and it won't release the energy that you need in order to stave off this gravity that's pulling inwards. Other questions?
Red shirt there. Go ahead.
I know through bombardment by protons, neutrons, that we can create heavier atoms than iron.
Yep.
What is to say those processes also don't occur within a massive star like that?
Okay, that's a great question. So the question is, we know that we can create exotic elements by bombarding nuclei with neutrons and protons. Shouldn't that happen in stars? And the answer is it does. And that is, in fact, how you make the heavy elements. So what you do is you take some iron nucleus or carbon nucleus or oxygen, and you fire a huge beam of protons or neutrons at it. Okay. And usually we think about neutrons, and what happens is the neutrons get absorbed by the nucleus, okay? And then they turn into a proton, by emitting a neutrino. Okay. And when that happens, you build up heavier and heavier nuclei. And the question is, where does that happen? And for the elements above iron on the periodic table, about half of them are produced, we think, in normal stellar evolution, kind of intermediate mass stars, 4 solar masses, 3 solar masses, 2 solar masses. I didn't talk that much about it. For the heaviest elements, and gold in particular, here is this same movie, except the color coding is different now, but it's the same movie I showed you before. And what happens is that the core collapses. Sorry, technical error. All right, I'll skip that. The point is that I want to go back to the other movie. The whole thing collapses. There's boiling and roiling, and the explosion happens. Okay? And after the explosion happens, it disassembles the whole star. And there's a wind, actually, that comes off the neutron star right after it's born. And that is filled with tons and tons and tons of neutrons. And so we think some of the heavy elements might come from this very strong neutrons you would get right here. So if I stuck you here at 10 to the 10 degrees Kelvin and densities of 10 billion to a trillion times your current density, you would absorb neutrons. And as you absorb neutrons, you would be transfigured from your stuff into interesting elements like strontium and yttrium and zirconium and possibly gold, europium, dysprosium, uranium, thorium, perhaps. We're not sure, but we think that's basically how it works.
Let's see, a fellow in the center here.
Any speculation on how the presence of dark matter would change nucleosynthesis?
Interesting question. The question is, how would the presence of dark matter change nucleosynthesis? There are several levels of answer. So dark matter pervades the universe. Dark matter is important for binding galaxies together. It's important for the evolution of the universe as a whole. And there are probably, although we can't be sure, dark matter particles moving through our bodies right now, just like neutrinos are very weakly interacting. It is possible that massive stars accumulate dark matter in their cores. And it is also possible that that might actually affect the evolution of the stars as they accumulate more and more dark matter, because it's a separate thing that you're adding into the mix that wasn't there before, and so it should change the evolution of stars. We don't know, is the answer. It could happen under certain models of what dark matter is. It could make a difference. In other models, it doesn't make hardly any difference. People are trying, if you could find a way that dark matter would affect a star, it would be a beautiful way to test models of dark matter, but we have not been able to do that yet.
You, sir, in the front row.
Would it be possible to unfuse
The question is, would it be possible to unfuse the elements fused by stars? Yes. So if you make very heavy elements, they can fission, they can radioactive decay, they can split apart into lighter elements. So that's a way in which nature unfuses very heavy elements. They become radioactive and they break into different pieces. You can also take a nucleus, like an oxygen nucleus, and if an oxygen nucleus was hanging around in space, it turns out that there's a bunch of very high energy particles roaming around in a galaxy called cosmic rays, and those very high energy particles can come in and bust up nucleus and essentially unfuse them into smaller nuclei. So yes, it is possible to unfuse the products of fusion in a star. Those we don't think are dominant in the sense most oxygen just came from the way that I just said it, but it's an interesting idea. Other questions?
Okay, you missed in the second row. Go ahead.
Hi.
So, like, can you pick up the iron that it makes?
So the question is, can you pick up the iron that it makes? So what you should think of is that have you been to the beach? Yes. Okay, so if you've ever been to the beach, you've seen sand. And if you've ever seen sand, it was made of silicon and oxygen and iron. And in each of those little sand particles, there are atoms of oxygen and silicon and iron. And all of those atoms were made in these big star explosions. And then they flew out into space. And then they kind of came together to make the Earth. and then you went on vacation and you sat on top of those little rocks. So yeah, you can't really pick up the atoms that are there.
Go user.
Can you,
Yes.
can you explain the 11-year cycle from the sun and the 22-year cycle?
The 11-year cycle and the 22. The question. Okay.
Can this happen in any star?
So the question is, can I explain the 11-year cycle of activity in the sun, and does this happen in any star, and presumably how is it related? So for example, the sun undergoes different levels of activity. It becomes more active and less active, and by that we mostly mean that it has more sunspots and less sunspots, and its large-scale magnetic field, the magnetic field of the sun, changes. Those processes are related to the structure of the sun, but not so much its fusion. They're not directly related to that. They're more directly related to its rotation and the convection going on inside it, which are partially driven by the nuclear fusion. So no, right now, with what I've said, I can't explain the 11-year cycle, but it's related to this magnetic dynamo going on inside the star, driven by its convection and rotation. So that's my answer to that.
Okay, let's take one more question. Oh, ma'am.
This is probably a tangential question.
It's all right.
With all these basic elements, carbon, hydrogen, oxygen,
Yep.
how do you explain some of the mechanisms of how these elements eventually form unicellular organisms, multicellular, and eventually plants?
Yes. So the question is, we start with these basic building blocks, carbon, nitrogen, and oxygen, and how do we get to unicellular organisms? That's a great question. I do not have a complete answer. But I will tell you a few interesting things. The first thing is that we see molecules in space. We see lots of molecules in space, and actually some fairly complicated molecules in space. So some simple molecules like carbon monoxide, carbon dioxide, other molecules. And we just have a telescope now called ALMA, which is looking for, when you look into space, you see whole galaxies like the Andromeda galaxy are emitting in the radiation of different types of molecules. And some are, very simple, but some would also be considered prebiotic from the point of view of the people who study that type of thing. I'm certainly not an expert. There has yet to be, I think, a discovery of discovery of many complex molecules. Let me leave it at that. So how you get from there, eventually, you make the Earth, okay, and all this stuff gets together, a process and subject of a separate talk I'm going to give, but the whole material comes together, and then somehow you have to take those building blocks and those complex molecules, probably, at least on Earth, with a big admixture of water, and then you need to make the creepy crawlies. And I don't know about the many steps in between, but I know that there are people here who are working on just that. In fact, a good colleague, a friend of mine, Dennis Bong, who's here in the chemistry department, is working on some issues related to that. And then there are some other experts in the room who I can see looking at me. But I don't know the answer.
All right, let's thank Todd again.